Chapter 8.2 Particle Accelerators and Detectors. So let's start with Chapter 8.2 Part 1 Particle Accelerators. By the end of this section, you should be able to describe the roles of electric and magnetic fields in particle accelerators. You have learned that an electric field can be used to deflect a charged particle, and also a magnetic field can be used to do the same. Now again, the electric field can also be used to accelerate a charged particle. We will see that. Now for example, if you have an electric field, if there is an electron, it will be attracted to the positively charged plate and it will be repelled by the negatively charged plate. So in this case, if it's a electric field, then always the electric field lines go from the positive plate to the negative plate, and the electron will be attracted in the opposite direction of the electric field. If it's a positive charge, it will move in the direction of the electric field. So this can be used to accelerate the particle. Derive an equation R equals P over BQ for a charged particle in a magnetic field. We will see this now. You may have to use the equations of circular motion to do this. We will see the details. Explain why high energies are required to investigate the structure of the nucleus. You have learned that the strong nuclear force holds the nucleus together. There are protons in the nucleus which are having the same charge, and because they have the same charge, they can repel. But what holds the nucleus together is the strong nuclear force. Even in chapter 8.3 you will see it. And then so you can see particle accelerators. We have the Linac, or the linear particle accelerator, the linear accelerator, in short we call it Linac, which accelerates the particles in a straight line. Then also we have particle accelerators which accelerate the particles in a circular or spiral path. One of them is the cyclotron, and from the name itself you can figure out. Now over here the name is Linac or linear. Linear means in a straight line. So here it's accelerating the particle in a straight line. Here you can see cyclotron, like cyclone, it's moving in a circular or spiral path. Cyclotron, a circular accelerator which gives protons about 1 mega electron volts of energy. These are the D-shaped electrodes. We will see the details, and we can find what F is using this method. Then we have the synchrotron, and what is it? A single ring accelerator like this is called a synchrotron. And over here, if you go to the definitions, you can see a synchrotron is a machine that accelerates charged particles around a fixed circular path. Now you can see all these are particle accelerators. Here you see the word accelerates, here you see the word accelerates, here also you see the word accelerates. A linear accelerator is a machine which accelerates charged particles along a straight line. A cyclotron is a circular machine that accelerates charged particles usually following a spiral path. Circular machine, okay, spiral path. A synchrotron is a machine that accelerates charged particles around a fixed circular path. Alright, so let's go into the details now. It's quite lengthy compared to the other lessons. Usually the other lessons have about 2 pages per subchapter, but here you have 1, 2, 3, 4 pages, basically like double. Alright, let's see. So then particle accelerators to investigate the internal structure of internal substructures of particle like nucleons. Now nucleons are protons and neutrons in the nucleus. Scientists collide them with other particles at very high speed. So what's the use of colliding? That is to investigate the internal substructure of particles, for example the nucleons. That's why we collide these particles. So scientists collide them with other particles at very high speeds or very high energies. It is necessary to use high energy particles because at lower energies the particles just bounce off each other. You have learned that proton is positively charged. So if you direct a alpha particle towards a nucleus, because the nucleus is containing protons, the nucleus is positively charged. So instead of colliding, it would just bounce back or bounce off. That's why we use a high energy. Now, for example, if it's an alpha particle, we give it so much kinetic energy that it collides with the nucleon or the nucleus. That's what this means. It is necessary to use high energy particles because at low energies the particles just bounce off each other, keeping their internal structure secret. If we can collide particles together hard enough, they will break up. So this can break the nucleus of the atom when you send particles at high energy, so that they won't be just bouncing off. Okay, break up, revealing their structure. In most cases, additional particles are created from the energy of the collision. Sometimes these extra particles reveal or confirm other new physics. The challenge for scientists has been to accelerate particles to high enough speeds. Charged particles can be accelerated in straight lines using electric fields. So I already explained it earlier. And their direction changed along a curved path by a magnetic field. So when we learn magnetic fields, we have already learned this, how to change how to deflect a charged particle using a magnetic field. You have learned the Fleming's left-hand rule also, that can be applied to find the direction that the particle is deflected depending on its charge and also the direction of the magnetic field. So let's look at the first accelerator, which is the linear accelerator. One of the simplest ways to produce energy high enough for these particle collisions is to accelerate a beam of charged particles along a straight path. Okay, so accelerate the particle that you're going to collide with something else in a straight line. However, this is limited by the maximum achievable potential difference. Now remember, greater the potential difference, greater the kinetic energy that is given to the particle. You have already seen this, the electron volt. Now if it was an electron here at rest, and then if you have the potential difference between, let's say, this end and this end, the potential difference through which the electron is accelerated, then we can find how much kinetic energy the electron will have once it comes to the other end. So let's say this is the positive end and this is the negative end. So if you have electron here starting at rest, once it comes here, it will have the maximum kinetic energy because it is accelerated through a certain potential difference, and that we found is EV, the charge of the electron times the potential difference will give you the amount of energy given to the electron, which is equal to the kinetic energy gained by the electron. We have seen this in a previous lesson. Now in this case, the particles, now here you can see they are electrons, but it may even be some other particle. So we will see it depending on the accelerator, depending on what they want to find, but basically it's easier to explain with the electron, so I say electron. And remember, the amount of energy is equal to the charge times the potential difference. If it was an electron, it's E times the V, the potential difference. So E is constant, the charge on an electron, that is constant. However, the amount of energy depends on V. So it is limited to the maximum achievable, the energy that can be given to the electron, for example, is limited to the maximum achievable potential difference. In order to overcome this problem, the particles are accelerated in stages. Figure A, you can see that here. So you have, first we accelerated it through this, then through this potential difference, like that we can accelerate it continuously to give it a very high acceleration. They are repeatedly accelerated through the maximum potential difference, making the particle energies very high. Using this principle, the 3.2 kilometer Stanford Linear Accelerator in the USA can accelerate electrons to an energy of 50 giga electron volts. So you can see it will eventually accelerate it through, if you accelerate it in parts, maybe one potential difference here, and finally the electron has gone through potential differences like totaling about 50 gigavolts. So times it by the charge on the electron, we get 50 giga electron volts, meaning they have effectively passed through a potential difference of 50 billion volts. Giga is what? 10 to the power 9. 10 to the power 9 is a billion. Okay, so 10 to the power 9 volts, or 50 into 10 to the power 9 volts. So it's 50 billion volts. Giga electron volts means so 10 to the power 9, that is a billion. 10 to the power 6 is a million, 10 to the power 9 is a billion. Okay, and you can see 3.2 kilometers. So how long, you can imagine how long this is. It's quite long. I think there are some diagram photos also of this linear accelerator. Maybe I can show you one. Okay, also if you just Google it, you can see some photos. Okay, did you know, Linac facts, despite being over 50 years old, the Stanford Linear Accelerator in California remains the world's longest linear accelerator. 50 years old. Longest linear accelerator. See, Linac. Linear accelerator. However, plans of the International Linear Collider are far advanced. Most likely to be built in Japan, this would consist of 2 linear colliders, each over 15 kilometers long, designed to collide electrons and positrons. Initially with energies of 250 giga electron volts, but with the design possibility of raising this to 1 tera electron volt. So tera is what? 10 to the power 12. So 1 into 10, or in other words 10 to the power 12 electron volts. If the particles to be accelerated by the linear accelerator in figure A are electrons, so here you can see, have a good look at this figure. The high frequency 3000 megahertz AC voltage. Now why is it AC, you might wonder. So what happens here is, let's say the electron is here. So when the electron is here, this will have a negative charge. Okay, so this side is negative. Then what will happen? The other side, can you see here? See, this side is connected to here, and then this side is connected to the other terminal. So that means if this side is negative, then this B should be positive. So once the electron is here, this side is negative, this side is positive, it will attract the electron this way, because the electron is attracted to positive, repelled by negative. Then once the electron comes here, what will happen is the current here reverses. See, AC voltage, the polarity reverses. So what will happen is, now B will be positive, B will be negative, and the one in front of that will be positive. So remember, it's the same connection to A also. So in the beginning A was negative, okay, and B was positive. Now what happens? B becomes negative, and then this C becomes positive, and A also becomes positive, we can say, because it's connected to the same terminal. A and C are connected to the same terminal. So when the potential difference or polarity here reverses, same thing happens here. So when the electron is now here, say here, B will become negative and C will become positive. So what will happen? It will accelerate through this gap. Okay, so C is negative, B is positive, electron is attracted to the negative side, repelled by the positive. Okay, then that process continues until all the way it comes out from here. I think it's explained here. I mean, there were some questions about the electric field and all here. We will go into those details also. Okay, so if the particles are to be accelerated by the linear accelerator in figure A, electrons, they are generated by an electrostatic machine like a Van de Graaff generator and then introduced into the machine. Once inside the cylinder, the electrons move in a straight line, as the electrode is equally attracting in all directions. So if you look at these electrodes here, these are all electrodes. Then inside that, they are attracting the same in all directions. So that's why Inside the cylinder, the electrons move in a straight line as the electrode is equally attracting in all directions. The alternate voltage supply is made to change as the electrons reach the middle of tube A. See? So it becomes negative. This repels the electron out of the end of tube A and onto tube B, which now has a positive potential. They accelerate towards it, and the whole process repeats as they pass through tube B and then accelerated on towards tube C. Okay, this carries on until the electron reaches the end of the line, at which point they emerge to collide with the target. So out here there is a target. In order to keep the accelerating particles that are moving faster and faster, so what happens is here it accelerates, then its speed keeps on increasing. That's why these tubes are longer. Otherwise it has to match this frequency, right? As soon as this comes out from here, the polarity of C and D should reverse. So that's why these tubes are longer from left to right. The particles travel through each successive one at a higher speed, whilst the time between the potential difference flips is fixed. Now see, potential difference flips is fixed, so it changes frequency at a changes polarity at a constant rate, maybe every half a second, something like that, for example. Flips is fixed as the alternating voltage has a uniform frequency of a few gigahertz, often referred to as radio frequency RF. This limit on the use of this kind of accelerator is how long you can afford to build it. Remembering that the whole thing must be in a vacuum so that the particles do not collide with air atoms, and it must be perfectly straight. Now remember, since we are accelerating it in a straight line, this has to be perfectly straight, and also we have to remove all the air from here. I mean, when this is built, so to remove all the air means to create a vacuum in here, because otherwise those particles will collide with air molecules that are here. So we need a vacuum, and also we need this to be straight. That's what they are saying. How long you can afford to build it. You need to make it, it should be very long. You can see here about 3.2 kilometers, and also there has to be a vacuum in here. Then it has to be in a perfectly straight line. Perfectly straight. So here the frequency is constant, so that means it changes the polarity every 3000 at a frequency of 3000 megahertz. Now if you want, we can find the period by taking the reciprocal of this number. Okay, then next one. Okay, then next one is, was Einstein right? One of Einstein's claims in his theory of special relativity is that nothing can accelerate beyond the speed of light. This means that particles in accelerators must be faced with a problem when they are already traveling close to the speed of light and then pass through a potential difference which should accelerate them beyond it. Okay, so Einstein said nothing can accelerate beyond the speed of light. So if you are doing this, then trying to accelerate with this kind of machine, when they are already traveling too close to the speed of light and then pass through a potential difference which should accelerate beyond it, then we can face some problems. So we will see. In 1964, William Bertozzi demonstrated that at very high speeds particles deviate from the equation. Now remember, I told you the charge of that electron times the potential difference through which it is accelerated by will give you the kinetic energy gained by the electron when it passes through that potential difference. Okay, so that is this equation. And indeed never accelerate beyond the speed of light. So at very high speeds the particles deviate from this equation, and therefore indeed never accelerate beyond the speed of light. So they can't go faster than the speed of light. By measuring, so who said this was actually Einstein. Einstein's claims in his theory of special relativity, one of Einstein's, is that nothing can accelerate beyond the speed of light. Okay, by measuring the actual speed of electrons accelerated from a Van de Graaff generator and then determining the actual kinetic energy by colliding them with a target and measuring the heat generated, Bertozzi was able to show that the energy imparted by the accelerating potential difference started to become more than the amount expected from the equation for kinetic energy. This demonstration showed that whilst the kinetic energy and momentum of the particles can continue to increase without limit, their speed does not. This can only happen if the mass of the particle seemingly increases with speed. This apparent mass increase becomes significant at speeds approaching light, known as relativistic speeds. Electron burst charge distribution as a function of time. So what happens is, when these reach the speed of light, these particles are coming closer to the speed of light, and we know that they cannot exceed the speed of light. So something should happen, right? So what happens is their mass increases. See, it showed that whilst the kinetic energy and momentum of particles can continue to increase without limit, their speed does not. So even if the speed is constant, if the mass increases, the kinetic energy increases. This can only happen if the mass of a particle seemingly increases with its speed. This apparent mass increase becomes significant at speeds approaching light speed, known as relativistic speeds. Okay, so electron burst charge distribution as a function of time. Now here we will see Bertozzi's experiment to demonstrate that nothing can accelerate beyond the speed of light. Okay, so here 1 meter, 8.4 meter drift space, one section of Linac. 15 mega electron volts Linac. Then oscilloscope, aluminium disc to stop electrons and signals arriving. To stop electron and signal arrival of electron burst at end of flight path. Alright, so here you can see cables transmitting signal of equal transmit times. Cable transmitting sweep signal, short tubes signaling start of electron burst down the flight path. Okay, so charging belt, window, photo tube, Van de Graaff pressure tank, fast pulse, electron gun, equipotential planes. The equipotential means they are the same potential. So this is what this person found. See, the solid curve represents the prediction of V over C whole thing squared. This one. According to Newtonian mechanics, V over C whole thing squared is equal to 2 times the kinetic energy divided by mass of, no, in this case it's an electron, mass of electron times C squared. Okay, so we can see this here. The dashed curve represents the prediction of special relativity. Here, this one, dashed curve. So you can see the same equation there. Mass of electron is the rest mass of an electron, and c is the speed of light in a vacuum. So is the rest mass of an electron, and c is the, so I think you already know it. And in a vacuum, the speed of light, so that is 3 into 10 to the power 8. The solid circles are data for Bertozzi's experiments. Here you can see solid circles here are the data of Bertozzi's experiment. The table presents the observed values of V over C. So here you can see the observed values. Okay, so you can have a look at this table. Then accelerating particles in circles. So far we saw how the particles are accelerated in a straight line. Remember, the acceleration occurs between the two cylinders, or in these are all cylinders are actually electrodes. Why are they called electrodes? Because you can see they are having a polarity. So at one time this one side is positive, at another time that same side will be negative. Then the electrode next to it will be having the opposite polarity always, and this is happening at a frequency of 3000 megahertz. So inside it will move at a constant speed, the particle, in this case the electron, but the acceleration occurs only between the two cylinders, or between the electrodes only. So in this gap it accelerates, this gap it accelerates, this gap it accelerates, but inside the electrode it will move at a constant speed. Okay, but because it is accelerated between the electrodes, when it goes from one electrode to the next, it will have a higher constant speed inside each electrode. That's why when you go from one electrode to the other, the electrode is longer. And remember, this frequency is constant. So once it comes here, once it is here, already the polarity has reversed, so that the acceleration can continue for the electron. Okay, that was actually one of the questions that was asked in the exam papers. Alright, now we will see accelerating particles in circles. As scientists urge such a struggle to produce ever longer linear accelerators, they sought to coil their accelerations up into a circle so that the particles could be accelerated in an electric field repeatedly in a smaller space. Now remember, this is quite long. It was about 3.2 kilometers long. So instead of doing something like that, where you will need a very large space, you can instead accelerate it in a circular or coiled or rather spiral way. So to coil the accelerators up into a circle. Now, for example, those who are taking biology would have learnt about the small intestine. So because it is all like coiled up, it can occupy a smaller space. Now, but if you put your small intestine in a straight line, it will be very long. So something like that. So this way we can minimize the space that we are using to produce the same acceleration by accelerating it in a circular path. See, as scientists struggle to produce even longer linear accelerators, they sought to coil the accelerations up into a circle so that the particles could be accelerated in an electric field repeatedly in a smaller space. To do this, we use the fact that charged particles moving across a magnetic field will feel a centripetal force. Now remember, due to that centripetal force, that charged particle will be deflected along a circular kind of path. It will be deflected in a circular path like this. Okay, and so will move in a circular path. We can work out the radius of the circular path and use it to construct a circular accelerator of the right dimensions. You can see here. Now for this you can use the Fleming's left hand rule. So you can start using it now. Use the Fleming's left hand rule. The thumb, the index finger and the middle finger should be perpendicular to each other. So we can try. Now first finger, that is the index finger, is in the direction of the magnetic field, which is into the screen or into the page. Second finger, that is the middle finger, should be in the direction of the current or the direction of movement of the positive charge. As you can see, it's along this path, right? So you can point it that way. Then you will see that the thumb points this way. The circular trajectory of a charged particle moving across a magnetic field. Note that the field lines can be shown coming out of the page by drawing a dot, and those going into a page like the magnetic field here can be shown by drawing a cross. So you have already learned this. Cross means into the page, circle and dot inside, that means out of the page. So I think you understand this is the path. Always the force is perpendicular to the direction that the charged particle is moving, and also perpendicular to the direction of the magnetic field. We have previously seen the equation for the force on a charged particle moving across a magnetic field in chapter 7. When we learnt about magnetic fields, we have learned this. That is, BQV. This is the magnetic force, BQV, force on a charged particle moving across a magnetic field. B is the magnetic field strength, also called the magnetic flux density. Q is the charge of the charged particle, V is the speed, F is the magnetic force. This force acts at right angles to the velocity V. You can see that is the arrow shown in red here. This force acts at right angles to the velocity V, meaning that the particle will follow a circular path. Recall that the equation for the centripetal force on anything moving in a circle is F equals mv squared over r. You have learned this equation. This is the equation for the centripetal force. F is the centripetal force. Now remember, centripetal force is not a force by itself. It takes the form of other forces. Now in this case, the centripetal force is the magnetic force. So we can set this equal to that. That's what is done here. So this force shown in red is the magnetic force, and it is also the centripetal force. Why it's the centripetal force? Because this is moving in a circular path. Remember that the centripetal force is an unbalanced force. Always it is a resultant or unbalanced force. Dividing out the velocity from each side, here we have v, here also we have p squared, so we can divide by v, and rearranging to find an expression for the radius of the circle gives r equals mv over bq. So mv is what? Momentum. So we can replace it with p. This means that for a given magnetic field, the radius of the path of a charged particle is proportional to its momentum. Now remember, b we can say is constant. That is the magnetic field strength or magnetic flux density. B is constant. Q is the charge of the charged particle. Let's say that's also constant. Then the radius here, radius of the circular path, here you can see r, it's labeled, is proportional to the momentum. Now momentum depends on the speed. If we say the mass of the charged particle is constant, so the faster it moves, we can say the greater is the radius. The radius of the path of a charged particle is proportional to momentum. At slow speeds, the radius is proportional to the velocity. Now remember, when the speed is high, that means when it's traveling to the close to the speed of light, the mass increases, because v cannot be greater than 3 into 10 to the power 8, which is the speed of light. So then at that point mass increases. So we are not talking about that one right now. Here we are telling at slow speeds the radius is proportional to the velocity or the square root of the kinetic energy. Now remember the equation, kinetic energy equals half mv squared. So if you make v the subject of that equation for kinetic energy, then we will have v equals something, and then we have to take square root. So square root of something, and the kinetic energy is inside that. Now in the kinetic energy equation, if you make v the subject of the equation, then you can see if you substitute it here, then it will have kinetic energy. So square root of kinetic energy. So r will be proportional to the square root of kinetic energy, or to the square root of kinetic energy. So you can even try that. You can make use the kinetic energy equation, make v the subject of the equation, substitute here, then you will see r is proportional to square root of kinetic energy. But as these experiments generally send particles at speeds approaching the speed of light, relativistic effects need to be accounted for. So here, since we are doing these experiments at approaching the speed of light, then we will have to consider the relativistic effects. Remember, the mass increases. In particular, at these very high speeds, the particle's mass appears increase. Particle's mass appears increase, which would also alter its momentum. Now remember, momentum is mass times velocity. So if mass increases, the momentum increases. The overall result is that a particle increasing in speed would travel along an outwardly spiraling path. Okay, so the overall result is that a particle increasing in speed would travel along an outwardly spiraling path. So what will happen is, when the speed increases, you can see the radius here increases, and momentum also increases. Mass also we can say when it reaches a certain speed close to the speed of light, it can't go beyond that, so the mass increases. So again the momentum increases and therefore R increases. We travel along an outwardly spiraling path. What do we mean by outwardly spiraling? Its radius increases. The radius of the circular path increases. So imagine it starts like somewhere here, then when it is going, that radius increases like that, something like that. Okay, so here you can see now we using this in the cyclotron. What is cyclotron? In 1930, Ernest Lawrence developed the first cyclotron, a circular accelerator which would give protons about 1 mega electron volts of energy. In a cyclotron, there are two D-shaped electrodes, or Ds. Those are these two, this one and this one. So this is the cyclotron. Okay, the structure of a cyclotron. You should understand this like you understood this one, the Linac, the linear accelerator. You have to understand the cyclotron also. Cyclotron, a circular accelerator which would give protons about 1 mega electron volts of energy. So here you see protons. In a cyclotron, there are two D-shaped electrodes, or Ds. Okay, so the acceleration occurs between the Ds. Now, we'll show you what happens is there is a magnetic field here, so it will come like this, and here it is accelerated. Okay, now due to the magnetic field, it will move in a circular path. But once it comes here, it will be accelerated because this is one electrode, this is another electrode. Then what will happen? Here it will be at a higher speed. Then like that, the radius keeps on increasing. Eventually, it will come out. We will see. Okay. Yeah, bombardment chamber open to air. See. In a cyclotron, there are two D-shaped electrodes, or Ds, and the particles are accelerated in the electric field in the gap between them. See, they are accelerated in the electric field in the gap between these two Ds. That means it's accelerated here. Like I told you over here, it is accelerated between the electrodes here. Similarly, here also it is accelerated between the two Ds. Whilst inside the Ds, the particles will travel along a semicircular path under the influence of the magnetic field. So there is a magnetic field here, so it will follow this kind of path. Okay, so remember there is a magnetic field. Imagine it's vertically downwards, upwards, so it will go in this path. Okay, so that will go like this, and here it will gain speed. Now it will go in a large circle like that. Maybe it's going, I think, this way, right? Anyway, whatever way, it's going in a circle. Yeah, whilst the particle will travel along a circular path under the influence of a magnetic field before being accelerated across the gap again, then another semicircle, another acceleration across the gap, and so on. As is each acceleration increases the momentum of the particle, the radius of its path within the Ds increase. So here, let's say it starts somewhere here, it goes like this, and so it goes like that, and then now when it's here, speed increases. So now it goes in a bigger circle. Then it's here, now it goes in a bigger circle. So like that, the circle increases. It spirals outwards, outward spiraling path. As each acceleration increases the momentum of the particle, the radius of its path within the Ds increase. And so it steadily spirals outwards until it emerges from an exit hole and hits the target placed in a bombardment chamber in its path. See, bombardment chamber open to air. So it comes out of here actually, I think. So for it to come out of here, this is actually not the proper place to place it, right? Maybe like somewhere here would be more effective because it goes like this. How can it come like that? Maybe if it was somewhere here, it can come out like that. Okay. Anyway, this is a diagram. This is just a diagram. South pole of magnet. Okay, so here you can see south pole of magnet, north pole of magnet. So the magnetic field is vertically vertically upwards. Okay. Yeah. First finger field. You can even use the Fleming's left hand rule here. Field, second finger current. Force will be this way. Yeah. North to south. Yeah. So I think it's going this way. Okay. Circling in the clockwise direction. Then only the force will be towards the center when it goes like this. You can try it with the Fleming's left hand rule. Remember, this is a proton, okay? It's going like that. So it's the same as the direction of movement of the proton is the same as the direction of the middle finger, the current. Middle finger represents the current in the Fleming's left hand rule. So then the magnetic force will be towards the center of the circular path. Alright. So voltage supply alternating, square wave PD. Now why this is alternating? Because when the proton comes here, this side should be now positive, this side should be negative, attract it that way to accelerate it. And then when it comes here, now remember earlier this is negative, now this becomes positive. So positive proton is repelled, this side is now negative. So that's how it accelerates. Similar to what I taught you here, the electrodes are switching polarity to accelerate the particle. Same thing happens here. The electrons are switching polarity to accelerate the particle between the electrodes. Lid of vacuum chamber, filament support and leads. Bombardment chamber open to air, so it would come out of here and collide with something. The particle comes out like north pole of magnet, D-shaped electrode, vacuum, tight thin window. To vacuum pump, this is to suck all the air out and create a vacuum in here, because otherwise when the particle is moving it will collide with the air molecules. Glass cylinder, okay. Cyclotron frequency. So this is the structure of the cyclotron. Now I think you know how it works, how it accelerates the charged particle, in this case proton. In order to maintain the acceleration at exactly the correct moment, exactly the correct moment, the PD needs to switch direction exactly when the particle exits from 1D to move across the gap between them. This means the voltage supply has to follow a square wave pattern where it flips polarity instantaneously. Okay, so I think this is self-explanatory. The frequency of these polarity switches only depends on the particle being used and the strength of the magnetic field applied. So you have already learned this equation for frequency. Frequency is 1 over period, and since this is going in a circle, we can say T equals 2 pi r over V. Now, why is that? You can think of it like this. Imagine there is a circle. Imagine it's going in a circular path, that proton. Okay, and this is the center. So when you go all the way around this, that is what? The circumference of a circle, right? Circumference of a circle is 2 pi r. Okay, so from here to here we will take it to be r, and the time taken to go one round is the period. So then what is that? The linear velocity, right? So velocity is what? Distance divided by time. Okay, distance divided by time, that is the velocity, or the speed is what? Distance divided by time. So all the way around this is what? Distance is what? 2 pi r. Okay. Divided by the time to go one round is the period. Okay. So V equals 2 pi r over t. 2 pi r over t. That's how you get this. So then T is equal to 2 pi r over V. During one complete period of the alternating voltage, the particle will pass through both these, thus completing a full circle at that radius. So it goes one whole circle. I think again you can understand this. So let's say the electron goes like this, 1, 2, okay, or rather like this. So we start here, let's say going once and coming here. So that means it passes, see, one complete period of the alternating, during one complete period of the alternating voltage, the particle will pass through both these, thus completing a full circle at that radius. So then you have this. Now what is this? Remember this, we saw it here. Okay, the magnetic force is the centripetal force. So from that only we get this, and once we have this, you can see that we can make okay, so MV is that. Now Now what are we doing here? We are substituting for r. See, r is equal to TV over 2 pi. So TV over 2 pi, right? We make r the subject, then r will be TV over 2 pi. Now substitute that here, TV over 2 pi for r, and then make t the subject. So 2 pi goes there, v goes down here, and then we get this 2 pi m over bv, because v and v cancels. So this is the period. And then frequency is 1 over period, so we take the reciprocal of this, you get that. Okay, if you want, you can write it and try it, you will get it. Okay, because we are using this equation. Frequency is 1 over period, then period is 1 over frequency. So if you take the reciprocal of this, then that is the frequency. Thus the frequency needed is independent of the radius, meaning that a constant frequency can be used and the particle will complete each semicircle through a d in the same time. That is, until the speed becomes so fast that the mass changes through relativistic effects. So here we just found the frequency, and you can see this equation for frequency doesn't have the radius, so the frequency needed is independent of the radius. So we can use a constant frequency, and the particle will complete each semicircle through a d in the same time. Okay, but remember, that is until the speed becomes so fast that the mass changes through the relativistic effect, because here you have mass. So the mass changes, then the frequency changes. Okay, then finally under this topic we have the synchrotron. Once the relativistic effects of mass increase are included in the equation for the cyclotron frequency, this is the equation for the cyclotron frequency. Now we will consider the relativistic effects of mass, and then we get this equation. So you can see the original equation. Now we consider the relativistic effects of mass increase into this equation, and then we get this. Note that m naught is the particle's rest mass. Now remember, when the speed increases, when it's close to the speed of light, the mass increases. As the frequency of the applied accelerating potential difference now depends on the velocity of the particles. So as the frequency of the applied accelerating potential difference now depends on the velocity of the particles. This means that uses cyclotron to generate high energy particles beams, it needs very clever circuitry to produce accurately timed polarity switches. The necessary electronics were first developed in 1945, and the synchrotron cyclotron can accelerate particles to as much as 700 mega electron volts. Alright, so I think you understand here, the V is here now. So because the V is there, the F depends on V. B and Q, we can keep them constant. Q is the charge of the charged particle, B is the magnetic field strength, and C is the speed of light. Those are all constant. But here you can see the speed V. Frequency depends on the speed. Okay, with the development of varying frequency for the accelerating potential difference, the next logical step was to vary the strength of the magnetic field using an electromagnet. So so that way we can vary the strength of it. This means that the radius of the particle's beam could be kept constant by simply increasing the magnetic field strength. Okay, so if you have an electromagnet, now remember, electromagnet, you can change the strength of the magnetic field by changing the amount of current in that electromagnet. So this way we can adjust the B. So the radius of the particle's beam could be kept constant by simply increasing the magnetic field strength in line with the increasing momentum. A single ring accelerator like this is called a synchrotron. Alternating tubes and bending magnets can generate very high particle beams, high energy particle beams. For example, the Tutor at Fermilab near Chicago in the USA could give particles 1 tera electron volts of energy. Tera is what? A trillion, 10 to the power 12. Alternate these rings can be used to store charged particles by making them circulate endlessly at a constant energy. Can be used to store charged particles by making them circulate endlessly at a constant energy. This is a particularly important use when trying to store antimatter, which will annihilate if it comes into contact with normal matter. So we have already learned, in the next section which is there, 8.3.1. Let's say you have a positron and an electron coming together, they annihilate. You will get 2 photons of gamma radiation when it happens. So the mass becomes energy. Ninovium, scientists sometimes cheat too. In 1999, the Lawrence Berkeley Laboratory in California published a paper claiming that they had produced an isotope of an element with atomic number 118. The paper claimed that they had succeeded in observing a chain of alpha decays following their collision of 499 mega electron volt krypton 86 into ions into a target of lead 208. So here you can see the diagram, krypton colliding with lead. The radioactive decay sequence was indicative of having started from element 118. Now see, now here you can see fusion. Okay, so starting initially named ninovium after the Bulgarian team leader Viktor Nunov. No other lab in the world was able to reproduce the results, and after a 2-year inquiry, it was determined that Nunov has falsified the results. The Berkeley lab retracted the paper, and Viktor Nunov, who has continually maintained his innocence, was fired. Okay, so that's not a real particle, but he came up with something like that. Anyway, there was nothing like this, they're saying. Okay, the fusion reaction which was claimed to produce element 118. Okay. Alright, so this last bit, in 2006, an accelerator facility in Dubna, Russia, working jointly with an American group from the Lawrence Livermore National Laboratory, claimed to have fused calcium-48 and californium-249 to produce the as yet unnamed element 118 with a mass number of 294. The team used a particle accelerator to bombard CF249 with high energy ions of calcium-48. With the previous problem surrounding this heavy element 118, the research team were very careful about the accuracy of their data, but it may be some time before the results are reproduced by an independent corroborating experiment. Californium is rare and highly radioactive. Mark Stoyer, a nuclear chemist at Lawrence Livermore National Laboratory who was part of the research team, said, "We saw something interesting and the way we were interpreted it's element 118, but you need someone else to duplicate it. A fundamental tenet of science is reproducibility." Okay, so that's the end of that part. Make sure you understand these definitions are important and answer all these questions.